All right, let's get through 2.6, which is moments and center of mass, a little bit more application and physics problems. So we'll start off with some point masses, and then we'll move on to something a little bit more continuous. Let M1, M2, M3, M4, all the way through Mn be point masses placed on a number line. So think of it like here's the ground, and there's 4, 5, or 6 different objects lying somewhere in a straight line. Or maybe not even just on the ground, maybe think of it like a seesaw. And then that's kind of what we're thinking about here. If you have some sort of seesaw, where should you place the pivot of the seesaw so that it's balanced? If you have a point here, point here, point here, point here, all on top of some seesaw, some of those objects might be heavier than others. So maybe your pivot should be right here to balance the seesaw so it doesn't kind of tip over one way or the other. That's the general idea. So those are called point masses placed on a number line. At the points, we're going to place their locations at x1, x2, etc. And then lowercase m is going to be the total mass of the system. So the sum of all of the masses, you just add up the total mass. How much does everything add up to? Then the moment of the system with respect to the origin, it's kind of like a weighted average is what we're kind of going for at the end of the day. This is capital M is going to be called the moment, and that's the sum of the mass times the location of the object. And then you're going to find the center of mass or the pivot of the seesaw by calculating the sum of the moments divided by the sum of the masses. And that's how that's always going to work out, the sum of the moments divided by the sum of the masses. So let's go through and do an example. Here's an example that we have. Suppose 4 objects or point masses are placed on a number line like so. I've got 12 kilograms placed at -4 is the location on the number line. That's just the location. We're going to say like the center is 0. And then so -4 just means these 4 meters to the left. And then I have another 12 kilograms placed at 4 meters to the right, so positive. And then I have 30 kilograms placed at 2 meters to the right, and then 6 kilograms placed at 6 meters to the left. We'll just say right is positive and left is negative. Find the center of mass of the system. I'm going to draw a picture because I think it's visual. This is another object example where you might not need to draw the picture, but I still think it's going to be helpful. So I'm going to label the locations. First, I had a -6, and at -6 is where I had a 6 kilogram object placed. That was that last one. And then it looks like I also have a -4. Let's label that. At -4, I had a 12 kilogram object. That was this guy right here. And then it looks like I also had a 2. So let me label that one a 2, and that was where I had, let me read it one more time. Where was it? Here we go. 2 meters was 30 kilograms. Okay, so that was my 30 kilograms. And then I also had a 4, and +4 was where I had another 12 kilograms placed. Okay, so now I've kind of drawn my picture with where everything is. 0 is the physical center of the actual object, but it might not be where the pivot of the seesaw is, because you can see it's certainly heavier in some places than in others. So let's find out where the center of that seesaw or the pivot of the seesaw should be to make it balanced. It might not be smack dab in the middle. So here's how we do it. X bar is what we're going to use as the notation for the center of mass. In this particular case, it's just one-dimensional. It's point masses. So the sum of the moments divided by the sum of the masses. And the moments are all going to be, I'm going to scroll up to remind us of that formula. The moments are all the mass times their location, and the sum just means add them all up. So that's what I'm going to do. The first one was 6 kilometers was at the location of -6. And then I had 12 kilometers at the location of -4, 30 kilometers at the location of 2, and 12 kilometers at the, I keep saying kilometers. I'm so sorry. Kilograms. I'm so sorry. Kilograms. I'm probably not going to re-record this video. You're going to have to deal with that. Kilograms was the mass. I'm so sorry. 12 kilograms at the location of 4. Sorry about that. And then we're going to take all of those and we're going to divide that by the sum of the masses, which would be 12 plus 12. I don't know why I did that in a wrong order. Let me fix that ordering. At least it was 6 plus 12 plus 30 plus 12. That was the masses. That was all the kilograms. not kilometers, kilograms. Okay, and then let's calculate that. I'm gonna get out my calculator and actually add that up. Let's see what we got. So I have a 6 times -6 plus a 12 times -4 plus a 30 times 2 plus a 12 times 4, and I ended up with 24 on top. And then I have a 6 plus 12 plus 30 plus 12, which is 60 on the bottom, and I can calculate that, and I got 0.4. Now, 0.4, what's really important to notice, this is kind of like a weighted average. This is how I'm going to calculate your grades at the end of the semester. That's not the actual center. That's the weighted average because some of them were weighted more. So where that is where the pivot of the seesaw should be built so that it stays balanced. So if I think of that on that picture, that means if this was the center 0, then at 0.4, this right here is 0.4, is where the pivot of the seesaw should be to make sure it doesn't tilt one way or the other, and that instead it stays balanced. Ta-da! Okay, let's do a little bit more. So the next part of this is extending this concept to a two-dimensional object, or again, kind of like a flat plate. But maybe that plate is not circular, because it's not always circular. Sometimes it is, sometimes it's not. Let's think about it if it's not a perfect circle. We're going to call it a lamina, which is just some two-dimensional plate that may or may not be a perfect circle, okay? If R is the region bounded above by the graph of f of x and below by the x-axis, and on the left and right side by x equals a and x equals b, respectively. Let's say rho denotes the density of the associated lambda. So rho is going to be the density of that plate, whatever it is that we have. Then there's 3 things that we're going to calculate. First is the mass. All right. The second one is going to be the moments. And then the center of mass is the moments divided by the mass. Okay, so kind of the same idea, but a lot more formulas just because we have more dimensions. And also we have to find the center of mass in the x direction as well as the center of mass in the y direction. So the center of mass now is going to be a physical point. It's going to be a location, and it's going to have an x coordinate and a y coordinate. So that's my end goal. Excuse me. Okay, let's do an example. I'm going to scroll back and forth to get those formulas for us, but hopefully you have those formulas with you in front of you. Let's do this example. You're going to need to draw a picture for this one, trust me. Sometimes you can get away without it, I know, but this one you're definitely going to need. R is the region bounded by f of x equals the square root of x, y equals 0, and x equals 4. Let's draw that picture. Square root of x function looks like this. Here is my f of x equals the square root of x. Y equals 0 is the x-axis, so that's easy enough to draw. I'll just draw that was my y equals 0. And then x equals 4 is remember, x equals a number is a vertical line, y equals a number would be a horizontal line. So it looks like my shaded region, just like we were doing earlier in chapter 2, is this guy. So this is like a plate that you have, like a physical plate. Think of it like an actual plate that you have in front of you that you're holding. And then like the goal is, it doesn't really matter what the plate looks like. I don't have a plate in front of me. Sorry, let's use this little object that I have that in front of me. And then I'm going to try to like, where should I place my finger so that it doesn't fall over? Where's the balancing point? And that balancing point, I'm looking for an x coordinate and a y coordinate. That's what I'm looking for here. So that's the general idea. So we're going to start off with the mass. That's the first thing. Then we're going to find the moments, and then we'll have our final answer. Okay, so not too bad. First things first is to find the mass. So I'm going to use lowercase m for the mass. I'm going to just write out the word mass. Sometimes that's more helpful. And I'll scroll up to remind you what the formula is here, because this one's a little bit more complicated because I have multiple dimensions here. I do want to point out really quick, you're going to want to open up the textbook for 2.6 when you're working on your homework, trust me, because it is very possible that you have 2 functions, like you have a top and a bottom. If you had a top and a bottom, then your mass would have the integral of the density of whatever the top minus the bottom is. And that would change some things. That was a dx. I'm sorry, that was a dx. That would change some things in the formulas throughout. So have that textbook open as you're working on the homework to get those different formulas involved. Okay, but in this case, I have only the one function. So it's rho times f of x. So my mass is going to turn into the integral of rho. And I have a constant density in this case. I should be really clear with that. The density is not given in the problem, which means you can treat it like it's 1. If the density is given, then use that number. But if the density is not given, you can treat it like the number 1. So it's the density times my function. My function is the square root of x, but because the density is not given, I can think of it like the number 1. So I'm going to do just that. And then my bounds are going to be, look from your picture, from 0 to 4, right there from the picture, you can see that the x values go from 0 to 4. Okay, and then I integrate that. I would probably rewrite that as the integral from 0 to 4 of x to the power of 1/2 dx. It's a little bit more obvious for me to integrate. Add 1 to the power, divide by the new power, evaluated from 0 to 4, etc. I ended up with 16/3. Okay, if you're willing to trust me, to make sure that you pause the video now and calculate it yourself. Did you get 16/3 as well? Pause the video now and calculate that yourself. That's important. Okay, but now that we've got the mass, the next thing is to find the center of mass. And so I'm going to need those moments. So I'm going to go through and do one thing at a time. I'm going to start off with my x bar, and then I'll find my y bar. Doesn't really matter the order. So it's m sub y over m. I just copied that formula down right here. But then I'm going to have to scroll back up and look at what was my m sub y. M sub y was the moment across the y-axis, is how you think of that, or in the y direction. So I'm going to go back and look at it. And this was the formula that I have for my m sub y. So that's what I need to plug in there. So I have to figure that out. We can do it. So my m sub y is going to be equal to, it looks like it's rho times the integral from 0 to 4, that was my a to b, of x times f of x dx, but my f of x, of course, is the square root of x. And density is going to be 1 unless you're given a density function. Cool? And then, of course, divided by the mass, which I already found to be 16/3. Okay, and then we calculate that. So that'll become 3 over 16 times the integral from 0 to 4 of x times x to the 1/2, which you can simplify. X times x to the 1/2 is x to the 3/2. And then I can calculate that. That'll become a 3 over 16, sorry, times x to the power of, add 1 to the power, that would become a 5/2 over 5/2 evaluated from 0 to 4. And if you're willing to trust me, I got 12/5. Pause the video and make sure you can get 12/5 on your own. Okay. Next one is y bar. Next one is y bar, which is m sub x over m. And I'm going to have to scroll back up and find the moment across the x-axis, which is, along the x direction, which is across the y-axis, if you will. Okay, here it is. Here's my m sub x formula. So I'm just going to plug and chug. I really, truly am going to just plug and chug. So I can treat rho as the number 1 because it was not given to me. So the integral from 0 to 4 of my function squared divided by 2 dx, and then divided by whatever I got for the mass. So 3 over 16, the integral from 0 to 4 of x over 2 dx. And so then this is going to become a pretty easy integral that would become 3 over 32, and then x squared over 2 evaluated from 0 to 4, etc., etc. Here I got 3/4. Cool. So what that means, now that you have your x bar and your y bar, that means that your centroid, so it's oftentimes called a centroid, or you can call it the center of mass, is the ordered pair 12/5, 3/4. Ta-da! This one's a little bit trickier, so as you're working on your homework, definitely maybe want to watch this video again. You certainly can. I also recommend that a lot of the homework problems for 2.6 have little videos attached to them to help you get extra practice. Watch those ones if you find yourself stuck. It's super helpful. All right, thank you guys. I'll see you next time.